this lesson, we're going to talk about the squeeze theorem. And to use the squeeze theorem, there are certain conditions that have to occur. Now, normally when I teach this lesson, we're in class. And last year I had a jar of coffee beans, and I had students guess how many coffee beans were in the jar. And eventually we got closer and closer and closer to the number, and we could figure out, like, if it wasn't 1,215, that was too small, and 1,217 was too big, that it was squeezed in between those. And so that's what the squeeze theorem is about. And we know that a function is lying in between other two functions, then we can find a limit. So our conditions are that all the functions we're talking about are continuous. So we have f, g, and h are continuous. And they're on some interval that contains a value a. And g of x is less than or equal to f of x, which is less than or equal to h of x. So it's saying that everywhere where on this interval we're talking about, that the f function is falling in between the g and the h functions. If there's a place on that interval where the limit as x approaches a of g of x equals the limit as x approaches a of h of x, and I know that f is falling in between those, then that's also going to be a place where the limit as x approaches a of f of x is equal to that same value, because it's squeezed in between there. So all three should have the same limit at that point. All right, so we're given the graph of f of x, g of x, and h of x. Oh, sorry, I forgot the steps. Okay, so to justify using the squeeze theorem, we have to show that the functions are continuous, which we will talk a whole lot about continuous functions later, but right now you basically can graph them without picking up your pencil. And so then what we'll do is identify the upper bound and the lower bound. We will evaluate the limits at the upper and lower bound, and then we will make a conclusion about whether or not we can use the squeeze theorem. And if we can find the value of that third limit. Okay, so we're going back to number one. We have the graphs of f, g, and h, and you can tell from the graph that h is falling in between g and f. All right, so it's squeezed in there. And so because they're all meeting at this one point, by that squeeze theorem, we can say the limit as x approaches 1 of h of x is going to be 1. And we could do that graphically even without the squeeze theorem. Okay, the next one, we need the theorem. So we are going to let g of x equal 4 minus x squared, h of x equal 4 plus x squared. And we know that f is falling in between g and h. We want to find the limit as x approaches 0. So all polynomial functions are continuous. So that's taken care of. All right, so we are going to start with the g function. So let's find the limit as x approaches 0 of g of x. And we can do that just by direct substitution. So I would plug in 0 for x, and I'm going to get 4. Okay. Then we'll go to h of x and see what we're looking for is this limit. So I don't know what f of x is, I just know it falls in between. So now I can find the limit as x approaches 0 of h of x. by plugging in 0 and getting 4. All right, so because these two are the same and f is in between those, then I can automatically say what we're looking for is that the limit as x approaches 0 of f of x is also 4. So if they're equal and the f is between, then it has to be 4, that same limit. All right, let's look at 3. We have also polynomial or quadratic functions, so they are continuous. I know that f is going to fall in between k and m. So let's just go ahead, and we're looking for the limit as x approaches -1 of f of x. So let's just go ahead and find the limit as x approaches 1 of k of x. So I'll take that -1 and I'm going to plug it into k. So I get -1, and then I get +2, and then I get +3, so that should be 4. All right, and then we're going to find the limit as x approaches -1 of m of x. All right, and the reason we keep doing -1 is because this is the limit we're looking for. Okay, so I'll plug it in there, and I'm going to get 6. So that isn't enough information for us to figure out what the limit as x approaches -1 of f of x is using the squeeze theorem. To use the squeeze theorem, those limits have to be equal. So we can't do it. So we would explain why. So because the limit as x approaches -1 of k of x does not equal the limit as x approaches -1 of m of x, the limit as x approaches -1 of f of x cannot be determined. There's an infinite number of values it could be. All right, and then we also can use a table to do the squeeze theorem. So we have a table of values that tells us that they're continuous functions. And it also tells us that k is going to fall in between f and g. We want to find the limit as x approaches 1 of k. All right, so we can look at the table, and when we're doing a limit from a table that is a continuous function, then finding the limit as x approaches 1 of f of x is really just finding its value on the table. That's just going to be 11. And then we can do the same thing for g of x. It's just the value on the table. So that's also 11. All right, so then we can use that and the squeeze theorem to find the limit as x approaches 1 of k of x. So it tells us to explain our reasoning. So let's just go ahead and do that real quick. So since f of x is less than or equal to k of x is less than or equal to g of x, and the limit as x approaches 1 of f of x equals the limit as x approaches 1 of g of x, and they both equal 11, we can say the limit as x approaches 1 of k of x is also 11. All right, so that's the squeeze theorem. You know that a function falls in between two functions that are continuous, and if the limit as x approaches whatever we're looking for is the same for the outer ones, then it's also that same limit for the inside one. So squeeze together. All right, so your assignment is going to be the topic 8.1 or the squeeze theorem worksheet that's also attached to this lesson.